All right, so we're going to start looking deeper into polynomials, and we're going to move towards something called the rational root theorem to kind of give you an idea where it comes from. Suppose you were asked to find the roots of this polynomial. Of course, you could take out the quadratic formula, although it's nice if you can factor, and I think the factoring part is a little bit more illuminating. Now, factoring these was never my strong suit when I was a student like you. So let me help you out. That's going to be 2x minus 3 times 4x plus 9. And if you're asked to solve for where that's equal to 0, well, that's not too bad. You're just going to set each one of these terms equal to 0 and then solve. So 2x minus 3 equals 0, or 4x plus 9 equals 0. In other words, move the 3 over and divide by 2, you get x is 3 halves, or x is negative 9 fourths. Okay, great. Now, why did I take you on this little journey here? Well, let's talk to you about the form of these answers. These numbers, when you do get rational roots, and by that I mean something which is an integer divided by an integer, these numbers actually are somewhat predictable. The numerators come from the factors of this thing, and the denominators come from the factors of 8. So, okay, what's that mean in general? Well, in general, where'd my hand go? Here we go. In general, when you're looking at a polynomial, let's call the factors of this p, and let's call the factors of this q. In general, if the polynomial crosses the x-axis at a rational root, it has to be a form of a factor of p divided by a factor of q, or plus or minus that. So, how do I want to state that? Let's see. Rational roots will be of the form plus or minus p over q, where p is a factor of this term and q is a factor of this term. Now, that can lead to a lot of possible rational roots. The usefulness of the rational root theorem has kind of waned over the years because of the increase in the availability of technology. I mean, you've got graphing calculators and decimals just to start things with. So it's not as useful, but it is still something that we are going to cover, something I'd like you to know. And it does come in handy a little bit. So let's take a look at p. P is the factors of 6, so that's these numbers right here. And then q is the factors of 105, and there's a lot of them there. So when you start doing plus or minus p over q, you get a lot of possible factors. The way I work these things is I'll start out with a 1 and do 1 over 1, 1 over 3, 1 over 5, 1 over 7. You've got to be methodical, otherwise you're going to miss something. And then do 2 over 3, 2 over 5, and so on. So you're going to get plus or minus all of these possible rational roots. That's not to say that your polynomial has to cross the x-axis at a rational root. It's saying that if it did cross at a rational root, it would have to be one of these. So let's take a look at our polynomial and see if we can make some headway regarding, well, where does it actually cross and what is it actually equal to? So if you're following along with the links, you can do that. Let's see, I want this one right here, and let's go back up to A. And maybe I'll zoom in a little bit. The nice thing about decimals is you can kind of click here and see where the roots are. Now, a couple of these we can kind of figure, well, what they have to be, but one of them just doesn't really look all that, all that exciting at all. So let's take a look at example A and see if we can't use the roots here to finish factoring this and clean it up a little bit. So One of the roots that I can see there is I've got a root at x equal negative 0.3333. And, can anyone think of a fraction that sounds like? What fraction does that look like? Yeah, looks like negative 1/3. And if you take a look at your list of possible rational roots, there's your 1/3. Remember, it's plus or minus this, so yeah, negative 1/3 is a possible rational root. Okay. So if I've got a root at negative 1/3, let's see. What's the corresponding binomial? Well, binomial would be x plus 1/3. Now, if negative 1/3 is actually a root, let's call this, let's write what y is. It's 105 x to the third plus 38 x squared minus 17x minus 6. If negative 1/3 is a root, what would happen if I put it in here into the polynomial? What should I get? 0. Should get 0. Now, the smart thing to do is to test that with synthetic division. So out front, I'll put the negative 1/3. Underneath, I'll have the 105, 38, negative 17, and negative 6. Remember, this last one here is your remainder. We're really hoping that's a 0. Now, speaking of zeros, this process of synthetic division starts with a 0. It's not written there for you. If it makes you feel comfortable, write it there. And we can add going down. We get 105. Multiply to go up. That's negative 35. Add going down. What's that give me?
3.
3. Multiply to go up. Gives me negative 1. Add to go down. Negative 18. Multiply gives me a positive 6. And bam, 0. That's great, because this kind of narrows down my problem a little bit. So this is your x squared, that's your coefficient of x, that's your constant term. And what this is really allowing me to do is to rewrite y. So I can write y as this. Y is going to be x plus 1/3 times 105 x squared plus 3x minus 18. Great. Now if I wanted to continue finding the roots of this polynomial, well, I already know where the root of this one is. I could just focus my attention on this one right here. And that's a quadratic polynomial. I could use a quadratic formula to solve for that. But we're going to be a little bit more clever than that. First of all, you might notice that in here there's a common factor of a 3. X plus 1/3. So I'm going to factor out that 3. That's going to leave behind 35x squared plus x minus 6. And now I'm going to distribute that 3 to this binomial out in front. And that binomial out in front is going to look different, but it's still going to have the same root at 1/3. You don't have to do that. It just looks better. You don't have fractions to deal with. Let's keep going. We were able to pick off that I had a negative 1/3 as a root. Is there any other easy low-hanging fruit that I can get from this? Well, let's look back at our graph. So that'd be this one over here. Yeah, nice. 0.4 is 2/5. Now let's just check something real quick here. Let's just check on our handout that 2/5 was one of the possibility, and it is. So far we've got a root at negative 1/3. That's one of our possibilities, and another one at 2/5. Keep in mind, these are just possibilities. They're not guaranteed to be a root, but we'll check it out. All right. So I'm not going to work with the whole polynomial. I'm just going to work with this one part. So let's see. X equals 2/5 is a root. That means x minus 2/5 is a factor. If I'm going to pursue this with synthetic division, it's going to look like this. 2/5 out in front, 35, 1, and -6. And let's take a look here. Start out with a 0 as before. I get 35. Multiply by 2/5 gives me 14. Add going down gives me 15. Multiply gives me a 6. And sweet. It worked out. I found another root. So that lets me rearrange my polynomial yet again. Hattie, what do these two numbers mean down here?
15 would be constant,
Mm-hmm.
and 35x.
Perfect. So what I can do now is I can rewrite y once again, this time as y equals 3x plus 1 times x minus 2/5 times 35x plus 15. Now there's nothing wrong with that at all. You can easily determine the last root here. Let me play the same game that I did just a moment ago. Remember how I cleaned this up a little bit? I factored out the 3. What can I factor out of this one right here?
5.
5. Cool. Cinco de Mayo. All right, let's take out that 5. X minus 2/5. Take out the 5. And that's going to leave behind 7x plus 3. Well, let's distribute that here. 3x plus 1 times 5x minus 2 times 7x plus 3. And that's perfect. You can now look at these and just read off the roots of each of them. We've got x equal -1/3, x equal 2/5. How about the last one? Can you read that one off? What would that be? -3/7. Beautiful. Notice that all 3 of these points are on your list of possible rational roots here. That one was right there. So, yay, nice. Now we went a lot farther beyond what was asked of us than we needed to, but that's okay. This is a good intro example to this stuff. How are we looking on this part? Doing okay with that rational root there? And we're going to practice it some more, a couple more times, but I like this. I mean, it's really nice, and it pairs well with your synthetic division, because when you use synthetic division, you start chopping down the problem. Notice we started out with a cubic polynomial, and then we got down to a quadratic polynomial. Well, that's easy to work with. You can use the quadratic formula on that one. And then we went even further and made it a linear problem, so that worked out great. All right, let's try some more here. So let's work with example B. And we're not going to go as deep in example B as we did with example A. So we've got p of x equals 2x to the 5th plus 9x cubed plus 6x squared minus 6. And again, you want to determine the possible rational roots here. So let's see if we can't do that. Now for the possible rational roots, I need to know the factors of the various numbers here. P is going to come from the factors of which number? The 2 or the 6?
6.
So the factors of 6 are 1, 2, 3, and 6. Yeah, P comes from the last number, Q comes from the first number. What are the factors of 2? 1 and 2. Nice. 6, by the way, is a perfect number because if you add up the factors other than 6 itself, 1 plus 2 plus 3 gives you 6. I think 24 is the next perfect number. After that, it's quite a ways before you get another perfect number. In any case, let's look at the possible combinations of plus or minus P over Q. So, again, be methodical in working with this. Start out with the 1. 1 over 1 is 1. And then you get 1 over 2. Then move on to the 2. 2 over 1 is 2. Do I need to list 2 over 2? No, because I've already got that. 2 over 2 is 1. I've already got 1. Move on to 3. 3 over 1. And then 3 over 2. I need both of those. And last but not least, let's look at 6. I'll get 6 over 1. Do I need to list 6 over 2? No, you don't. Let's not forget something that I'll make sure you remember, which is the plus or minus. This could be positive, these could be negative. So all together we have 12 different ones. I'm really happy if you take the time to write it in order. There's actually a surprisingly large number of orders you could write this in. There's 720 different orders you could write these 6 numbers. So, wow. It makes it easier on me when you put them in order. I'm not going to ask that you necessarily do that. So it'd be 1/2, then 1, then 2. No, how about then 3/2, then 2, then 3, then 6. So you might get an appreciation point from me if you take the time to write them in increasing order there, but don't count on it. Don't count on it. It is appreciated either way, though. And that's it. Just looking for the possible rational roots. If we take a look at the actual polynomial itself, we can find out, I don't think that it actually crosses the x-axis at any of these. So if you look, it really only crosses the x-axis at one place, and that's not on our list. So wherever it crosses, it's an irrational number. Okay, no big deal. Notice that it only crosses at one place. But I know that with a third degree polynomial, there's going to be 3 solutions. The other 2 have to be complex. So you got 1 real and 2 complex solutions there. Nice. Okay, how are we looking on example B here? Doing okay? Let's keep going. Example D. Where's no, missing. One second. Let's just deal with these. Okay. And actually it might be easier to see here. It says find all the real zeros of the polynomial, use the quadratic formula if necessary. Enter your answers as a comma-separated list. It's including repetitions. That's kind of an annoying thing for me, the way they have this set up. But we'll take a look at it. We'll start by figuring out what are the possible rational roots. And then we'll see what that tells us and see if it helps us along the way to finding all of the zeros. So finding all of the zeros is what we did in example A, where we actually found them, not just list them, not just factor them, but we actually found each of those values. So let's see if we can't do the same thing with example D. Start by figuring out what the rational root theorem says. What's the P? What's the Q? Find all the different possibilities of plus or minus P over Q. When you get that list, turn to a neighbor. See if they agree with you. Thank you, Reagan. So let's shut this one off. You know, we skipped an example, didn't we? We skipped example C. That's all right. We'll come back to it. Okay, so the factors of P and Q are kind of small set, because both of these are prime numbers. P has to be, what's our choices for P? 1 and 7. And Q has choices of 1 and 3. If you do plus or minus P over Q, that's going to be plus or minus this set. 1 over 1 is 1, 1 over 3, and then 7 over 1, and then 7 over 3. So if this graph crosses the x-axis at a nice integer or at least rational value, it's going to be from this set. If you actually take a look at where it crosses through the x-axis, then I think we'll be able to figure out which one it actually passes through. Bam. Gotta love decimals. It's so easy. So it passes through at -1. Let's see how that helps us. So example D, we've got a root at x equal -1. This polynomial, P of x equals x, just give me 3x cubed plus 5x minus 5x minus 7. A root at x equal -1 corresponds to what is a binomial? X minus 1, x plus 1. There we go. Out in front, though, when I do my synthetic division, I'm going to put the -1, 3, 5, -5, and -7. Assuming this is a root, what should I get here as a remainder?
0.
0. Well done. So speaking of zeros, we'll start out with a nice little goose egg right there. That gives me 3, -3, 2, -2, -7, 7, and bam, 0. Okay. This allows me to rewrite P of x as x plus 1 times something. Somebody fill in for me what that something is.
X squared plus 2x minus 7.
Good. It's just coming directly from here. That's your coefficient of x squared, x, and your constant term. So 3x squared plus 2x minus 7. Now suppose all we're really interested in is trying to figure out, well, where does this cross the x-axis? Finding the roots of this polynomial. Well, we can finish this by setting it equal to 0. And that's going to equal 0, well, where this equals 0, of course we already know where that happens, right? That's at x equal -1. Where does 3x squared plus 2x minus 7 equal 0? if you're like me, I was never very good at factoring these things. So if we can't factor it, what's the alternative to solving here? Quadratic formula. Good. In case you need a quick refresher on that, let me scratch it off to the side. X is negative b plus or minus square root of b squared minus 4ac over 2a. Long time ago, I heard somebody sing the quadratic formula to the tune of Pop Goes the Weasel. I can't get it out of my head since then. So, in any case, let me fill in the quadratic formula here for us. So that's going to be negative of 2 plus or minus 2 squared minus 4 times a, which is 3, times c, which is negative 7, over 2 times 3. All right. So it's not going to necessarily work out nice and even, which is probably why I couldn't see a way to factor it. Negative 2 plus or minus the square root of, that'd be what, 88 over 6. Square root of 4 times square root of 22 is the same thing as the square root of 88. And that allows me to factor out a 2 once I clear things up underneath that radical. It's really tempting here to cancel the 2 into the 6, but I can't. I can't do that. Instead, what I got to do is I got to be a little bit more careful here and factor out the 2 from the numerator. Jason, if I factor out a 2, what's left?
Square root of 22.
A little bit more than that. I got the plus or minus square root of 22. But if I distribute, I don't get what I started with. So what else am I missing here?
-1.
Yeah, -1. All right. Now that I got multiplication, this times this in the numerator, now I can cancel. 2 cancels into the 6 3 times, and it leaves me with -1 plus or minus the square root of 22 over 3. Yay. So a little bit of work with the quadratic formula, and we're okay there. Let's take a look at the roots. As far as listing them in WebAssign would be concerned, you'd have to list -1, comma, -1 plus the square root of 22 over 3, and -1 minus the square root of 22 over 3. Suppose you didn't do so well on the last test and you're like, man, I better make sure these are right. How could you make sure that these are right? What's one way? Say using decimals. Well, I see that -1 is right. How about that one? Is that right? Is this one right? How could I check those?
You could calculate one.
Yeah, thank you, ladies. You can put them into your calculator and make sure that it actually works. So let's clear this out. And then if you're going to do this without being fancy, you type in -1 plus the square root of 22 in parentheses, exit the square root, and then put your right parenthesis divided by 3, and bam. Now if you're looking at it like, I really don't feel like typing all of it in again to get the negative root, then don't. Hit the second key, then the enter key, and bam, it pulls up your previous calculation. Now I just go back and change the positive to a negative. Nice. If you look at the decimal values here, they match the decimal values that we're seeing on Desmos. Here and here. On the exam, these are the answers that I'm gonna want. Although, unlike WebAssign, I'll let you give me plus or minus root 2 over, or root 22 there. You don't have to write it out one then the other. Nice, nice. How's that one looking? Jacqueline?
When you factor out the 2, what happens to like the 2 out in front of the square root of 22?
This one? Maybe to make that a little easier to see what's going on, let's try this first. So negative 2 plus or minus 2 square roots of 22 over 6. Would it hurt if I put this as negative 2 times 1? Is that kind of the same thing? All right, and then now I'm just taking out the 2. And it's going to leave behind the negative and the 1. And it also leaves behind plus or minus the square root of 22. Another way to see what's going on there is this idea that when you factor something out, what you're really doing is you're dividing both terms by that factor. So, you know, kind of following up on that one, if I add, let's see, negative 2 plus or minus 2 square roots of 22 over 6, when you factor out a 2, you're really dividing each of those terms by 2. Let me put that 2 in a different color. So when you simplify, negative 2 divided by 2, that gives you your negative 1, and then the 2 cancels there, leaving you with the square root of 22. So one way or another, you're going to be left with a negative 1 plus or minus square root of 22. Which way did you like better, the first way or the second way? Second way? Okay. All right. Sydney, then up front.
Do we take all the P over Q values and test them all?
We did not. Yeah. The reason we didn't bother testing all of them is because we had a nice graph, and you could look and say, well, all right, well, I'm pretty sure it's negative 1. Now, back in the day, before all my students had a graphing calculator, or at least access to one, we did have to do a little guess and check. It's like, okay, well, it could be all these different values, and then you would guess, and you'd hope you hit one. In fact, there's something that I don't teach anymore. It's called the upper bound theory, or upper bound theorem, and lower bound theorem. But if you were to guess at a root, and when you did your synthetic division to test it, if all of these numbers ended up being positive, that would say that your root is too high, or your guess is too high, that choose something to the left as your next guess, because you don't want to go to the right, it's too high. But there's just really not much point in it anymore, because you can look at all this technology and get, you know, your answers pretty quickly. Yeah.
You went from square root 88 to square root 4 and square root 22. How did you do that?
4 is a perfect square. If you take a look at the left-hand side board, I've got our list of perfect squares there. 4 is the largest perfect square that goes in here. So 4 goes into 88 22 times, right? 4 times 22 is 88. But then, the nice thing about having the 4 out front is I can take the square root of it. So that's why I chose to split it up. Yeah, I factored it out. Mm-hmm. Yeah, so, you know, another example would be if you had like the square root of 72. Well, the largest perfect square that goes into that one is 36. 36 goes in there twice. So then it becomes 6 square roots of 2, which is nice. It's simplified greatly. The way you work with that list is you always try and find the largest perfect square. Because a lot of times people go, oh, 72 is 9 times 8. And yeah, that's true. But then you got to play around with 8. Oh, 8 is 4 times 2, and this is 3 times 2 times square root of 2. You eventually get to the same thing, but it's a lot of extra work. So I would suggest going with the largest perfect square that goes into your number evenly. All right? Yeah, good question. Let me take a look back at example C, see if it's worth doing example C. It probably is. Just overlooked it. Yeah, C was on the front side of this. Says find all the real zeros of the given polynomial, they're integers, and then write the polynomial in factored form. Now this one, given all we've done, is a piece of cake. Let's take a look at this in terms of the graph. So, let's zoom in a little bit. There we go. 1, 2, and 3. Beautiful. So we've got roots at -7, 1, and 2. So let's write those down. Our roots, x equal -7, x equal 1, x equal 2. What's the corresponding binomial? X plus 7, x minus 1, and x minus 2. If you look at the behavior, remember bounce, wiggle, and straight through? What does it have to be for each of these? Straight through, and straight through. Now you associate that with a multiplicity of 1. So overall, what's the degree of our polynomial? Yeah, it's a degree 3 polynomial. And I hope you remember from the other day that if you have an odd degree polynomial, it's either going to look like this or like this. And in our case, it certainly looks like the former. So if we put this all together, we can write that as x plus 7 to the first power, x minus 1 to the first power, and x minus 2 again to the first power. So there it is, nice and factored, and we can look at that and we already know what the roots are. So, wow. Hey, wait, let's give it some love.
That was easy.
Yes. All right. How are we looking on example C? Okay there? Was it easy? Was I lying? That was easy? All right, awesome. Appreciate the feedback. Let's move down to example E. And it's always useful to take a look at the graph. Down here. Okay. So there's the graph. Let's see what the rational root theorem says about this polynomial. Where could it cross the x-axis? Well, P has to come from what set of numbers? What are my choices for P? All right, so, well, that's your, yeah, 1, 2, and 4. And Q is just 1. Well, that's pretty nice. So as far as plus or minus P over Q is concerned, it's going to be a small list, plus or minus 1 over 1, 2 over 1, and 4 over 1. So if it has any rational roots at all, it has to pass through here, these points. Let's pick it up on another sheet of paper with example E here. And don't want that one. Or that one. P of x is x to the fifth minus 4x to the fourth minus x cubed plus 10x squared minus, or plus 2x minus 4. Ooh, a lot going on with that one. Let's see if we can't get a handle on one of the roots. Something that I can put in there to get a 0 out of it. Let's take a look at our graph. And it looks like -1 is a root. Pretty confident about that. So, okay. Let's see then. X equal -1 is a root. Let's use synthetic division, get rid of that root at -1, and then kind of pare down our problem. Now, we actually have a quadratic equation that'll solve quadratic problems. There's also another formula which gets much messier for cubic equations, and there's even one for fourth degree equations. But I've never seen anyone use that one. It's just awful. And interestingly enough, they proved, a mathematician by the name of René Galois proved that you can't solve this for a general formula to solve the quintic equation. Just can't. The interesting thing about him is that he wrote down his proof the day before he was shot in a duel.
Wow.
Yeah, at age 22. Yeah, yeah, pretty wild.
Boys will be boys.
yeah, that's more than boys. He was actually kind of set up. He was a little bit of a political radical, and he was kind of set up in a duel with somebody who was much better than him. Anyways, let's keep going. So it's going to be -1, 1, -4, -1, 10, 2, -4. All right. What do I expect when I'm all done here?
A 0.
A 0. Let's see if we get that. So a 1, a 1, -1, -5, 6, 5.
What?
Let's see, wait a minute. -1, oh, how about a 5 there? My bad. Yeah, I'm looking ahead too much. Let's. All right. 5, and then a 4, -4, 6, -6, -4, +4, and that's what I wanted. I wanted a big goose egg down there. Awesome. That allows me to rewrite this polynomial. No longer am I going to regard that as all this. I'm going to regard that as P of x is, what binomial corresponds to x equal -1?
X plus 1.
X plus 1 times all this stuff. Now remember, that's going to be your constant. That's your term in x, x squared, x cubed, x to the 4th power. So it's going to be x to the 4th minus 5x cubed plus 4x squared plus 6x minus 4. Whew. All right. So I promise not to give you anything of degree 7 or higher. LOL. Probably 5 or less. This becomes, even 5 becomes a little bit tedious. But let's just do this a little bit more, see what we can come up with. There's 2 more roots that we can actually figure out without too much fuss. And let's see about one of them. Well, how about the root at -1? What can you tell me about the root at -1? What's its multiplicity, Hattie?
2.
2. Why? Why 2? It has a bounce, right? So what that means is that we can play the same game again, except with a smaller polynomial. So let's use x equal -1, -1 again, except with this polynomial. What should I write underneath here, Ava? What would I put underneath here for my second polynomial? Or my,
-5, 4, 6, -4.
perfect. Now that last one is going to be a remainder. It should be a 0 like it was before. Let's see that that works. 1, -1, -6, +6, 10, -10, -4, 4, and 0. Yay. So I can rewrite p of x again. P of x is now x plus 1 times x plus 1 times something. Ella, what's that something?
X cubed minus 6x squared plus 10x minus 4.
Perfect. Let's go fishing for some other coordinates as well. Now, by the way, you probably won't write it as x plus 1 times x plus 1. What's another way to write it? X plus 1 squared. All right. Let's go fishing for some other coordinates here. Other easy zeros. Well, that doesn't look like one. Oh, x equal 2. That's another easy 0 here for us. So let's get rid of that from our polynomial. Now I'm going to work with the reduced polynomial here. So x equal 2 is a root. 2 goes out in front. David, what should I put underneath here, please?
1, -6, 10, and -4.
Perfect. Thank you. Add going down. 1, 2, -4, -8, 2, 4, and 0. Yay. Awesome. Nick, can you help me rewrite p of x one more time?
P of x is going to be x squared minus x, -4x plus 2.
Good. X squared minus 4x plus 2. There's also this stuff out in front here. We have the x plus 1 and the x plus 1 up here, which I wrote as x plus 1 squared. And there's one last little piece that I got to put here.
X minus
Minus
2.
2.
Our x minus 2, corresponding to this term right there. All right, so we've greatly simplified this down to the point that, yeah, you're not going to find any more rational roots here. So if I wanted to solve for where this equals 0, well, I know a couple of places where it equals 0. It equals 0 at x equal -1 or x minus 2. But this last one, what am I going to do with that? Yeah, the quadratic formula. With all kinds of enthusiasm. I hear it in your voice. The quadratic formula. All right. Quadratic formula gets used a lot more than you might ever imagine. All right. Let's see here. So it's going to be x equals a negative of something plus or minus the square root of something squared minus 4 times something, all over 2 times something. Now the reason I'm putting in all these parentheses is because, in particular with a negative value for b, it's very easy to make a mistake here. It's very easy to miss the fact that you've got a double negative right here, or that you're squaring a negative and that should get a positive. And then times a 1 times a 2 over 2 times 1. So if we carefully account for that double negative, we'll end up with 4 plus or minus the square root of 16 minus 8, which would be 8 over 2. Okay. Let's clean this up a little bit. This is going to be 4 plus or minus square root of something times square root of something else. Square root of 8 splits up into square root of 4 times square root of 2. Yep. From the numerator, I can factor out a 2. Can someone tell me what's left if I factor out a 2 there? Thank you, ladies. 2 plus or minus the square root of 2. Those 2's cancel. So that's nice. And I'm just left with 2 plus or minus the square root of 2. Yay! Sort of. It's a long one, all right? But we've now got all of our roots here. So the final tally on our roots would have to go like this into WebAssign. We had a root at -1. And in fact, we had a root at -1 twice. So you have to list them both with a comma. -1, comma, -1. And then there was a root at 2, and 2 plus the square root of 2, and 2 minus the square root of 2. Now, for me, on a test, you can get away with 2 plus or minus square root of 2. You don't have to list them separately like that. If you want to, that's great too. But this is good. This is what I'm looking for. This is what WebAssign will be looking for. Now, you can kind of confirm these if you wanted to. You could look at the graph. The decimal value of 2 plus the square root of 2 should be about 3.414, and you can make sure that it goes through the graph at that point. But other than that, I think we're pretty good on this one. Yes?
In regards to the equation itself, do you just leave the end piece as x squared minus 4x plus 2?
Yeah, I mean, if you really wanted to, we could write that in a factored form, but it would involve these square roots and it just look kind of ugly. So, yeah, I'd leave it like this. Yeah. Good question, though. Thank you. Anything else on example E here? All right. Let's turn our attention to example F. And let me see if I can't get us a better graph here. Yeah, that looks pretty good. Here, no. Boy, these are ugly looking. Did I copy the right graph? Example F. Let me take a look at the handout here. Thank you. I knew there had to be something wrong there someplace. So minus 5x cubed.
Plus 8x plus 4.
Boy, I just got this whole thing wrong, didn't I?
Oh, it was
There's also meant to be
minus
5
x.
4.
There we go. Let's start over. P of x. Someone want to read that to me?
X to the 5th
X to the 5th
minus x to the 4th
minus x to the 4th
minus 5x cubed
5x cubed. Keep going.
plus x squared
Mm-hmm.
plus 8x plus 4.
All right, that's looking a little bit better. All right, and we do have some nice integer components. Let's take a look back and see what the problem is asking us. It says find all the real zeros, enters a common rate of separated list. I would add one more thing. I think we should be able to write this in factored form. So let's see if we can't do that. And let me find my copy of the handout for that one. No, I don't have it. Just a cheat here. So let's see here. We've got roots at -1 and 2. All right. We'll see if we can reverse engineer this a little bit. So our roots are at x equal -1 and x equal 2. Julian, what are the binomials that correspond to these roots?
X plus 1,
X plus 1 and
x minus 2.
perfect. Next thing I want to think about is the behavior. So, Robert, up front, what's the behavior of these? Bounce, wiggle, or straight through? Starting at -1. All right, got a wiggle, perfect. And then what's happening at 2? A bounce. Nice, thank you. Now those correspond to some multiplicities. So Sean, what multiplicities do these correspond to?
Odd and then even, so you can do like a 3 to the first one, and then a square to the second one.
Cool. So in total, we've got something of degree 5. Let's see if that's going to match for us. Our polynomial, at least to this point, we could write as x plus 1 cubed times x minus 2 squared. Now, does this have the right shape for this kind of a polynomial? Well, that goes back to your end behavior stuff. So we're dealing with something of an odd degree, so we can zoom in past the even degree stuff. Is it going to have a positive leading coefficient or a negative leading coefficient? Which one does our graph look like? The one on the left or the one on the right? It has a positive leading coefficient, so we don't need to put anything here. Just understood to be positive. There's your factorization, and there's your roots. Nice. Okay, 2 more. Again, we're going to kind of reverse engineer these. I'm going to give you a chance to reverse engineer these. If you're watching this later at home, then pause the video and see if you can't race ahead and figure out the polynomials here. So the first thing I want to do is I want to decide what are the roots. Didn't want this, I want to write. So let's look at the roots. This is going to have roots at x equal -2 and x equal 1. Then the binomial, the behavior, and finally the multiplicity. So fill in this chart for both of these. Roots, binomial, behavior, and multiplicity. That should eventually lead you to P of x. What is P of x for each of these? These are good problems because they blend a lot of the stuff that we've been doing with the end behaviors and the correspondence between roots and factors. It pulls a lot together. I like these. So some of the software I get stuck using is kind of low tech. And so what I'll do, because I can't easily do a pause, is I'll just do kind of like a manual pause. So here's my pause button. If you're watching this later, just zoom on past this until it's done pausing. I'm gonna walk around a bit, see how you guys are doing on this. If you have any questions, let me know. Were you just waiting for me to do this?
Yeah.
Okay. All right. Try it yourself. Almost. Take a look at and okay, good. Keep going.
I played it for that's why I didn't start playing until
That's not straight through. That's your straight through. You should try and catch it straight through. Okay, so let's see what we got here. Starting with this one, the binomial is going to be x plus 2 times, and x minus 1. The behavior, we've got a bounce and a wiggle. And how about over here? What kind of multiplicity do you associate with a bounce? 2 and a wiggle, 3. Now, it could be 4, 6, 8, or whatever, but generally we go with the lowest number that we can. Overall, we have a degree of n equal 5 here, and that makes sense when we start putting this together. X plus 2 squared times x minus 1 cubed. But this has the wrong end behavior. If you have a positive leading coefficient, then it should go down to the left and up to the right. But this has the opposite behavior. So you need that negative out in front. That negative is worth 2 points. So make sure you catch that. Yeah, all right. Let's look down here. Again, roots at -1 and 2. Well, actually not again, I guess. It's a little bit different. So x plus 1 and x minus 2. What's the behavior at -1?
Straight.
Straight through, nice. And that has a multiplicity of? 1. All right. How about this one? Root of 2 has a wiggle, and awesome. Multiplicity of 3. Degree, altogether, the degree has to be 4. So if we put that together, it's x plus 1 to the first power. I'm not going to write to the first power. It's understood. And x minus 2 cubed. Now, if you have an even degree, it should face up unless it has a negative leading coefficient, in which case both tails of this function will face down. Since these are both facing down, once again, you have to have a negative out in front of your polynomial there. Whew. All set. How are we looking on section 3.4 here? All right. Let's call it a day on this section.